Draw a square. Draw a circle inside it, touching all four sides. Now throw darts at the square completely at random. The fraction that land inside the circle is the ratio of the two areas, which works out to pi over 4. So multiply that fraction by 4, and you have estimated pi. Without measuring a circle, without any geometry, without ever writing down what pi is, just by throwing things and counting. That is Monte Carlo, and it is the most general problem-solving technique in this entire series. This is the finale, and it ties everything together. Today, the 3 ingredients every Monte Carlo method shares: estimating pi in 4 lines, how to know when your estimate is good enough rather than guessing, the square root law that governs what precision costs, and an honest account of when this approach is the wrong tool. Every Monte Carlo method, no matter how sophisticated it looks, has the same 3 parts. 1. A way to generate random inputs from the right distribution. 2. A deterministic calculation you run on each one. 3. An average over all the results. That's it. Financial risk models, particle physics simulations, rendering engines, and film. Same 3 steps, wearing different clothes. The reason this matters is that it works on problems where analysis simply cannot go. As soon as your problem has more than a handful of interacting random variables, or a decision rule with conditions in it, or a payoff that depends on the whole path rather than the endpoint, the closed-form solution usually stops existing. Monte Carlo doesn't notice. If you can code the process, you can measure it, and the code barely gets harder as the problem gets uglier. So let's do it properly. We generate 100,000 random x-coordinates and 100,000 random y-coordinates, uniformly between -1 and 1. That 100,000 darts landing anywhere in a 2x2 square, with no bias toward any region. Then one line does the rest. A dart is inside the unit circle if x squared plus y squared is at most 1. That gives a Boolean array, and taking its mean gives the fraction inside. Multiply by 4, and you have pi. Notice the structure. Generate, test, average. Exactly the 3 ingredients from a minute ago. Run it with 100,000 darts, and we get 3.1416. Correct to 4 decimal places. Now, this is a genuinely terrible way to compute pi, and I want to be clear about that because there are algorithms that give you millions of digits. The point isn't the answer. The point is that the same 4 lines work on problems that have no formula at all, and pi is simply a case where we can check the answer. Here's the estimate as darts accumulate. Wild at first, swinging well away from the true value, then tightening onto the dashed line. And this is the same shape we saw in episode 1 with the coin flips, and in episode 5 with sample means. It's the same law each time. Simulation converges, and the way it converges is predictable. Which lets us answer the question that separates a demo from a working tool. How many samples do I actually need? The standard error is the standard deviation of your samples divided by the square root of n, and that gives you a confidence interval for free. So don't pick a round number and hope. Run until the interval is tighter than the precision you need, then stop. That turns simulation from guesswork into measurement with a stated uncertainty. And here is the cost, which is the single most important practical fact about this method. To get 1 more decimal place, you need 100 times more samples. 10,000 samples gives you 2 digits. 1,000,000 gives you 3. 100 million gives you 4. Every decimal costs 100-fold, which is why serious Monte Carlo work is mostly about variance reduction, techniques like importance sampling and control variates that get more precision from the same number of samples rather than just running more of them. The honest caveat: a simulation inherits every assumption you built into it, and it presents them back to you as a confident number. Assume returns are normal and your risk model will be blind to crashes, exactly as we saw in episode 4. Your confidence interval describes sampling error only. It says absolutely nothing about whether your model of the world is right. That's the failure mode behind most famous risk disasters, and no amount of extra samples fixes it, because running the wrong model more times just gives you a more precise wrong answer. So let's close the series. 14 episodes and really one idea. Probability questions have two routes. Derive the answer, which is exact and elegant when it's available, or simulate the process, which is approximate and works on almost anything. We learn to simulate, to check convergence, to test hypotheses by shuffling, to fit and to be suspicious of what we fitted, and throughout, to plot the thing before summarizing it. If you can describe a random process precisely enough to code it, you can measure it. That's the whole series. Go and simulate something. Thank you for watching.